Today's video, we're going to talk about noble gas electron configuration and Lewis dot structures and how the periodic table can help us understand the electron configuration of elements. So let's get started. As we talked previously, the chemical properties of elements are determined a great deal by the electrons and their arrangement and how those electrons are arranged in the atom. And since the chemical properties are determined by the arrangement of the electrons, and the periodic table is arranged based off of the chemical properties of the atoms or of the elements, it's easy for us to say that the periodic table itself will tell us a lot about the electron configuration and help us write that. So if you remember from the last video, the long, complete electron configuration is kind of cumbersome and kind of a pain to write out, but there is a shorter way and there is a trick to looking at how to do it. And so that's what we're going to talk about moving forward today. All right, so if you remember, the s orbital has two electrons that make up the or can fill up the s orbital. It can hold up to 2 electrons total because it has only one suborbital. Now the s block on the periodic table that we talked about when we discussed the periodic table, the s block consists of the first 2 groups, columns 1 and 2. All right, so when you look at the periodic table here, you have groups 1 and 2 are the s block. So 1s, and of course helium is over here with the noble gases because it is a stable element. However, we know that because of its electron configuration, it has only 2 electrons and they're in the 1s orbital. We can say for electron configuration purposes, helium belongs right here. So you'll notice that the groups 1 and 2, you have 1s, 2s, 3s, 4s, 5s, 6s, 7s. These are the periods, and this is the s block, all right? So the p block, p orbitals, have 6 electrons. They have 3 suborbitals. Each suborbital holds 2 electrons, so they can hold a total of 6 electrons. Now, those 6 electrons correspond to the 6 groups of the periodic table that we call the p block. All right, so you have the p block over here is these 6 groups, 1, 2, 3, 4, 5, 6, 6 groups there, and this is the p block. These fill the p orbital. All right, 2p, 3p, 4p, 5p, 6p, and we will discuss a little bit more about that in just a bit. The d block is made up of the middle ones, and the d orbital has those 5 suborbitals and can hold 10 electrons. And so when you look at the d block, you'll notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. Each column corresponds to one of those electrons that the d orbital can hold. Now, I do want you to also notice here that this is labeled 3D, even though it's in the 4th row. Remember, we talked about the Bohr model and the iron, it not being completely correct in that instance because the way that we did the Bohr model. But the 3D orbital is actually a little bit larger than the 4s orbital, and so it extends out past it a little bit. And so this is the off-ball order that we talked about on the last time. So 4s and then 3d. So the d block here, you'll notice that the d block, we have our row -1, and we'll talk about that more in a little bit. And then our f block, the f orbital has 7 suborbitals, each one holding 2 electrons. So the f orbital holds a total of 14 electrons. And those 14 electrons correspond to the 14 groups down here in the lanthanides and actinides, the intertransition metals. Down here at the bottom, there's 14 of those. So we have the 2 columns of the s orbital. We have 6 columns for the p orbital, 10 columns for the d orbital, and 14 for the f orbital. That's why these are called the s, p, d, and f block of the periodic table, because they correspond to the orbitals that make up the electron configuration. All right. So let's see how this can help us in writing electron configurations. We're going to write out a couple of examples and see how to use this idea of the blocks telling us where things are on the periodic table to get a couple of examples. All right, so now as you look at the periodic table here, I also have here the off-bar diagram that we talked about before, and so what I'm going to show you is how the off-bar diagram and the periodic table are related. So thing you need to remember, as we talked about just a minute ago, the D block, you're going to have your row minus 1. So if it's in row 3, or row 4, I mean, period 4, you're going to subtract 1, so this would be 3D. If you're in row 7, this would be 6D. All right, so you need to make sure that you remember that. And then your F block down here is going to be your row minus 2. So you'll notice that these are right here. So they actually belong here in row 6, because you'll notice that's 56 and then 57. So this is actually row 6. If you wanted to write that on yours, you have row 6 and row 7. So this right here is row 6 minus 2, so that's 4F. And this one would be 7 minus 2 is 5F. Okay? So when you look at that, if you, if you look at your periodic table, you've got 1s, and so again the helium is right here, so we fill up 1s, and then we have 2s, and then 2p, and then 3s, and then 3p, and then 4s, and then 3d, and then we have 4p, and then 5s, and then we have, after 5s comes 4d. And so you'll notice that the off-bar diagram follows the periodic table. So if you remember the row minus 1 and the row minus 2, and you just go in the order on the periodic table, you don't actually need this. All right, you can just use the periodic table. And so what's helpful about this is figuring out the last term of our electron configuration, right? Because we just fill everything up until we get to that last term. Well, so let's pick an element, and let's just do, say, silicon. All right, I'm going to pick silicon's number 14. All right, well, I'm going to write it out the full electron configuration for silicon. It has 14 electrons, so I'm going to do 1s2, 2s2, 2p6. That's 10 electrons. I still have 4 more to go, so I'm going to have 2p6. After 2p comes 3s2, and then 3p. Well, I've used 12 of my 14 electrons, so this has to be 3p2. Okay? Now, that's drawing it out the long way, going through and counting. But I don't actually have to do that if I know what this last term is whenever I start. And that's the power of the periodic table here, is it tells us what the last term is when we start off. So, let's pick another element. Let's do, say, we'll do tellurium, 52, Te. All right? Well, let's look at where tellurium is. It's in the 5th row. It's in the P block. And in the P block, notice the P block starts right here. So this is the first element in the P block. So it's 1, 2, 3, 4. So it is the 4th element in the P block. So it's 5p4. This is the last term of tellurium's electron configuration. So if I ask you to draw out the full electron configuration for tellurium, you're going to start at 1s, and you'll do 1s2, 2s2, 2p6, and you just fill up everything. And you just write out the full electron configuration for all of it until you get to 5p4. Everything else here is full, and if you stop at 5p4. Now, if you do it in the correct order and you write the correct numbers there, then all of those numbers should add up to the number of electrons of 52. And that's the shortcut, or that's the easy way of checking your answers in the periodic table and knowing how the periodic table shows you where things are. So the off-bar diagram, the off-bar sequence is actually in the periodic table if you just look at the rows and whatever. So you'll also notice that the first row only has an s orbital. So the first energy level only has an s orbital. The second energy level has an s and a p. The third energy level has an s, a p, and a d. All right. The fourth energy level has an s, a p, a d, and an f. And so if you think back to the Bohr model, the first energy level could only hold 2 electrons. Well, it only has an s orbital, so that's 1s2, 2 electrons. The second energy level could hold 8, if you remember, and so we've got 2 right here from the s orbital, and we have 6 right here from the p orbital. That's 8. All right. The third energy level could hold 18. Well, that's our s is 2, our p is 6, that's 8, and then our d was 10, that's 18. So 2, 8, 18, and then the fourth, fifth, and sixth energy levels had a p orbital, or sorry, an s orbital, a p orbital, a d orbital, and an f orbital. All right, and s had 2, p has 6, d has 10, f has 14. That adds up to a total of 32, which is why when we talked about the Bohr model, we said the first energy level had 2 because it was just the s orbital. The second energy level could hold 8 because it was an s and a p. The third energy level could hold 18 because it was an s, a p, and a d. And the fourth, fifth, sixth, and seventh energy levels could hold 32 because it was an s, a p, a d, and an f. So all of that information is right here on the periodic table, which is why the periodic table is an amazing tool. And this is how we use the periodic table to find the last term of an electron configuration. All right, so let's do one more. Let's say we're going to do barium. Well, barium is in row 6. It's in the s block, and it's the second element in the s block. So barium's electron configuration is going to end with 6s2. So you would write out the electron configuration. You would start at 1s, and you would follow the sequence: 1s, 2s, 2p, 3s, 3p, 4s, 3d, all the way through until you get to 6s2. And then you stop because you would be done. All right, so let's move on. That's the long, drawn-out way of finding the last term, and then you write out the full, complete electron configuration. And so now we're going to move on to a shorter way of doing it. So now that we've seen these examples of using the periodic table to make a help us with the electron configuration, have the full, complete electron configuration, there's a shorthand way to do that, because the electron configuration is really long and cumbersome, especially for large elements like uranium or Einsteinium. They have lots of electrons, and so you've got a really long, complete electron configuration. That's kind of cumbersome to write down. So we're going to use a shorthand way, and it uses the noble gases. Since the noble gases constitute the last column of the periodic table, column 18, it's also, as you move across the rows of the periodic table, as you move across, you get all the way to the end. The noble gases are the last element in a given period. And then once you get past, like say you're at argon, once you get past argon, it moves over to the next row, which would be potassium. It goes down to the next period. So each noble gas represents the last element in that energy level before you go on to the next energy level, and then start those repeating patterns of properties again. So we use the noble gases as a shortcut in writing the electron configuration. Instead of writing out the full electron configuration, we use the noble gas as a way of shortening it. All right, so let's see how this is done in an example. I'm going to do a long, drawn-out one, and then we're going to do a short one. All right, so to do a noble gas configuration, the first thing I'm going to do is do a full, complete electron configuration for an element. And I'm going to do strontium. Let me get a different marker here. I'm going to do strontium. Okay, so when I look at my periodic table, I'm going to use the stuff that we just talked about using the periodic table. Strontium is right here, so it's 5s2. So I know that I'm going to end with 5s2. So I'm going to write out the full electron configuration for strontium, starting with 1s. So I do 1s2, 2s2, 2p6. So after p comes 3s2, and then 3p6, 4s2, 3d10, 4p6, 5s2, and that's where I'm going to stop because that was the last term. So this is the complete electron configuration for strontium. Okay. Now, for the noble gases, as we just said, they are the last term in the last element on each row. So if I want to do strontium's noble gas configuration, I need to find the noble gas that comes just before it. So the way to do that is I'm going to move up one row and all the way over to the end, because this is number 38. So xenon is 54. It comes after strontium. So I want the noble gas that comes just before strontium. So I do that by going up one row all the way over to element 36, krypton. All right. So I'm going to write out the full electron configuration for krypton real quick so you can see the point that we're going to make and why this is a shortcut. All right. So krypton is in period 4, p block, 6th element. So krypton is going to end, I'll go ahead and write this out. Krypton is going to end with 4p6. So I'm going to write out the full electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then I'm done because that's the last term for krypton. So when I write all that out, you should hopefully see that now we have that is exactly the same as that. All right, so the majority of strontium's electron configuration is the same as krypton's. So we have a shortcut way of doing this now. Instead of writing out all of this, knowing that this is the same, we're simply going to write the symbol for krypton in brackets. So what this means is I'm going to use krypton's krypton's electron configuration, and then all I have to do is add on what comes after that. Okay, so krypton plus 5s2. This is strontium's noble gas configuration. Krypton's the noble gas. So it's the noble gas configuration of strontium is krypton 5s2. Okay, let's do one more example. I'm not going to write out the full long drawn out thing, just show you the shorter way to do it. So let's pick one. Let's say let's pick astatine. Okay, astatine is right here. It's At. All right, and it is in period 6, p block, and it's the 5th element. So we know it's going to end with 6p5 because it's period 6, p block, 5th element. Okay. Now the noble gas just before astatine, go up one row and over, is xenon. So what I'm going to do is write the symbol for xenon in brackets. Now xenon is at 5p6. It's 5 p block, 6th element. So it's 5p6. Well, what comes after that is 6s2, and then after 6s we have to come down here to this one is 4f 14, and so I have to go all the way through to the end of this. Then I'm back up here to lutetium, all right, and that's in the 5d, because remember, the D block we subtract 1 from the row, the F block we subtract 2 from the row. Okay, so this is 5d 10, and now I get to 6p, and so this still is kind of long, but it's a whole lot longer than if I'd started at 1s and wrote all of that out, and wrote out 1s2, 2s2, 2p6, 3s2, that, and gone all the way through until I got to the 5p. This is much shorter, much less to write down. It's the shorter way to do it. So I start with xenon, and then I fill in from xenon to where I need to end. So this is why it's very important to know what that last term is also. Now, I do want to clarify that that last term of the electron configuration, based off of where it is, that is not actually 100% accurate. Not all elements follow the off-ball rule exactly, but for a basic chemistry class, that's good enough for what we need to understand. You do need to understand, though, that and if you're somebody who's a chemist watching this video and you are saying, that's not right, that's not right, that's not right, I know that it's not right. But it is a good enough basic understanding for somebody who's not going to study chemistry for a living. If you are going to study chemistry for a living, then you will need to learn the differences and what is not exactly right about that, and that's for another day, another time, and another teacher. Now that we've drawn and written out the complete electron configuration, and we've done a couple examples of the noble gas electron configuration, which is a shorter way, let's actually get into talking about what we really need to know about, and that's Lewis dot structures and these outermost electrons. So when it comes to everyday chemistry, the stuff that we do on a regular basis, the electrons that we really care about are the ones on the outside, those outermost electrons. Now, the ones on the inside, the inner shell electrons, they matter because they affect how those outermost ones actually behave. But the ones that actually do the reacting, the ones that are actually involved in the chemistry between atoms, are the ones on the outside. So we're going to worry mostly about the ones on the outside. And as we discussed previously, those are called valence electrons. So those valence electrons, the ones on the outer edge, are the ones that we really care about. Now, valence electrons in actuality are not just the highest energy ones, but they're the s and p orbital electrons in the highest energy level. So whatever that highest energy level is, it's the s and the p orbital electrons in that highest energy level. That's what we define as the valence electrons. So the maximum number of valence electrons you can have is 8, because the s orbital can have 2, and the p orbital can have 6. So 2 plus 6 is 8. So the most valence electrons you can have are 8. And that's very, very important. That number 8 is extremely important in the bonding and how chemistry happens and how the elements actually react together. So it's really important that you notice that the S and the P are 8. Which is also why the S and P block are the representative elements, because that 8 valence electrons makes a big deal about how things react and the chemical and physical properties. All right, so a Lewis dot diagram shows these valence electrons as dots arranged around the element symbol. It's just a way of writing down the element and showing how many valence electrons it has. It's a really simple process, but you do need to be able to utilize this for elements, because when we start talking about chemical compounds and how those bonds form, these Lewis dot structures for elements are going to be very, very helpful in figuring out how they bond correctly whenever they create chemical bonds. So let's see some examples on how to draw Lewis dot diagrams or Lewis dot structures. So to draw a Lewis diagram, a Lewis dot structure diagram, is really, really simple. The only thing you need to know is the element symbol and the number of valence electrons. So let's start with a simple one. Let's do helium. All right, helium, if you don't know, we look on the periodic table. Helium symbol is He. Okay, and it has 2 valence electrons. Yes, it's in group 18, but remember, it's the exception to the group number thing. It belongs over here. It has 2 valence electrons. So we're going to draw those, excuse me, we're going to draw those 2 valence electrons as dots. Now, since helium only has the 1 energy level, the s orbital, as we learned from Hund's rule and all of that, they're going to pair together. So we're going to draw helium's dots paired together like this. Right? So this is the Lewis dot structure for helium. Now, sometimes you'll see people who will do it like this, where they separate them. That's totally fine. You could also do it like this, where they are on opposite sides. But it's helium with 2 dots. Those dots represent its valence electrons. That one's pretty simple. All right, so let's try another one. Let's do the element tin. All right, tin symbol is Sn. Okay, so it's here in group 14. So group 14 means it has 4 valence electrons. And actually, based off of what we just talked about, it's got the 2s here, and then it's got 2 in the p. So 2s and 2p, that's 4 valence electrons. So for 10, I'm going to write the symbol Sn, and then I'm going to write the 4 valence electrons. 1, 2, 3, 4. Now I usually always start on the right side and go counterclockwise. It doesn't really matter. There's not like a right way to do it and a wrong way to do it yet per se, as far as what direction you go. But I do that just so that we know that we are going one dot at a time. So remember that Hund's rule, they're going to fill one at a time. So we're going to do one dot at a time as we go around. We've used all 4 of them. So that's 10. 10 is pretty easy. All right. And so let's try radium. Radium is just Ra. And if you look at the periodic table, it's here in group 2. So it has 2 valence electrons. So 1, 2. That's it. These Lewis dot structures are really easy to draw. They're really easy to do. They're also really easy to screw up if you're not paying attention to the number of valence electrons. But they're really easy to do. And so let's do one more. Let's do astatine, which we did the noble gas configuration for earlier. So let's do astatine. It's AT, and astatine is here in group 17. So it has 7 valence electrons. Okay, so I'm going to start here. I'm going to do 1, 2, 3, 4, 5, 6, 7. Now notice I paired them up. And if you wanted to, you could think of it kind of like you're doing a square around your symbol, but don't actually draw those lines. But you're doing a square around that, and you're just drawing those dots on that square. All right. But you do one at a time, and then you pair them up, and so that shows you that you've got 3 pairs of electrons and then 1 unpaired electron. And this is actually important to how the chemistry actually happens. And that's why we're doing this Lewis diagrams right now, because when we do bonds and we talk about how chemical bonds form, then how they form here is going to matter, or how the valence electrons are arranged matters to how they form bonds. So this is our Lewis diagrams. All right, so that's it for today's lesson. So in the next lesson, we're going to talk about atomic emission spectra and what that is and what that means. So thanks for watching, and have a day.